Right, this is the Grandmaster video for Chapter 8, Sections 1 and 2. A person can swim 9 meters upstream against the current in 10 seconds. With the same amount of effort, the person can swim 23 meters downstream with the current in the same amount of time. Write a system of linear equations that will determine the person's swimming speed, as if in still water, and the speed of the river current in meters per second. So what we have going on here is a person is swimming against the current, so they're fighting against the river current. They can cover a distance of 9 meters in 10 seconds. But if the person turns around, okay, they're swimming just as hard, but because they've turned around and they're swimming with the river current, they can actually cover a much greater distance, in this case 23 meters, in the same amount of time. All right, now to model this situation using a system of equations, we need to create some variables. So might as well create them for the two quantities that we're looking for, and that is the swimming speed of the person. So that's how fast they would be swimming if the river was completely still, so in still water. And also a variable for the speed of the river. So let's create a couple of let statements. So let person's swimming speed, I'll call that, I don't know, P for person. And let's let the river's, the current speed. I'll call that R. At this point, we want to create two different equations, and each equation is going to model each scenario up here. So in case 1, when the person is going upstream, we're going to create an equation using P's and R's. And then in this situation, where the person is swimming downstream, we'll create another equation, again using P's and R's. All right, so I'm just going to split this into two parts. So over here is anything upstream, and over here is anything downstream, just to keep things separate. Okay, so when the person is swimming upstream, let's say this way, speed is P, hence the river is flowing this way at speed R. Downstream, okay, well that means the person is going this way at speed P. The river is still flowing in the same direction. Okay, so this is R. Okay, so the overall speed, or should I say relative speed, to someone standing on the shore watching you, well, here, if you're going upstream, so I'll just say relative speed, so that's how fast you appear to be traveling to someone watching you from land. Because these are in opposite direction, it's the difference between the two. And hopefully that makes sense to you, because if you were swimming against the current at the exact same speed as it was flowing against you, someone watching you from the shore, to them, it would look like you're not even moving at all. You'd just be flailing your arms in the water and not going very far. Okay. Whereas over here, because you're traveling with the current, right, to a person watching you, it looks like you're traveling way faster. They think you're a super swimmer. But in reality, the current is pushing you along. Okay, so that would be P plus R. All right, at this point, we have everything we need to construct our equations, apart from just one thing. And that is, what is the relationship between the distance traveled, the speed at which you're traveling, and the time involved? Well, distance is equal to average speed times time. Well, in this problem, we are assuming that the speed is not changing, so distance in this case is speed times the time. Okay. Well, the distance in this scenario upstream, we are told, is 9. We know that our speed is P minus R, and the time is 10. So we can construct our equation now. You can write 9.0, but in this case I'm just going to write 9. Remember, this is an equation, so I don't want to put in any units. So 9 equals P minus R, and times the time, that's just 10. Okay? We don't have to do anything more, but if you want, you can expand this out using distributive law, and this would give you 10P minus 10R. Right? When we're traveling downstream, we're given a different distance, and that is 23 meters. So that's 23 equals, but we're using this relative speed, so it is P plus R. And the time, well, it says here the same amount of time. So again, it is 10 seconds. Okay, so we were only asked to create some equations, so this is fine, but I guess you could expand this out if you want to. But the point is we're just trying to create a system of equations, and we've done that. Right? Here they are. We'll solve these later on. Okay. So when we use different techniques that you will see down the road, when you actually solve for P and R, you'll actually be able to figure out how fast is the person swimming and how fast is the current flowing. So there we go. A jeweler makes silver pendants by melting two metals together. He mixes sterling silver, 92% pure silver by mass, with pure silver to make an alloy that is 94% pure silver by mass. Write a system of linear equations that will determine how much sterling silver and pure silver is needed to create a 75-gram pendant. Okay. Now, modeling this problem using a system of linear equations is actually not very easy. I would argue it's one of the more challenging ones. I really had to think about this one. But it's a little bit easier if you just break it down step by step and, well, first decide what are our quantities, what are our variables that we need to, create. So we're looking for sterling silver and pure silver. So we need to figure out how much we need of each. So let amount of pure silver, okay, so in grams we'll say, so in grams, we'll call that P for pure, however many grams we need. So we got to mix that with a sterling silver, but how much? So we're going to let the amount of non-pure silver, so this is the sterling silver, okay, in grams as well. We'll let that be S. S for sterling. Okay. Now, how on earth can we use quantities P and S to create a system of equations? Well, one of them is actually not that difficult, and that's actually right here. We know that however much of pure silver and sterling silver we combine, in the end we want a grand total of 75 grams. So that's actually pretty easy. So we just know that P plus S has to be 75. Okay, this is in grams, okay, but I don't need to write the units because this is just an equation, okay, but we made sure that P and S were both in grams. Okay, so this is our first equation. That wasn't too bad. Okay, so the next equation is not as easy to get, okay, but we have to create a second equation because if I only had this one equation, there's an infinite number of combinations of mixing pure silver and sterling silver to create a pendant that weighs or has a mass of 75 grams. But if I was just to pick two numbers that added up to 75, I can pretty much guarantee that the concentration of pure silver would not be correct. Okay, so you have to use the right amount of each. So that's actually where the key to the second equation lies, is we have to get the amount of pure silver correct. Okay, well, pure silver here is just pure silver. But we know in S, we know that whatever S is, 92% of that is pure. So to find that, you just multiply S by 0.92. So the amount of pure silver from P is just P, plus the amount of pure silver in the sterling silver, well, that's just 92% of whatever S is. So that's 0.92 S. Okay, that amount of pure silver added together has to be 94%, so 0.94 of the 75 grams. So remember, when you want to calculate a percentage of a number, you just express the percentage as a decimal and then multiply it by that number. So 94% of 75 is just 0.94 times 75. Okay, so this is the second equation. Okay, so this is the amount of pure silver plus sterling silver has to add up to 75. And the amount of pure silver from the pure silver plus the amount of pure silver within the sterling silver, because it's 92% pure, that has to be 94% of the 75 gram pendant. Okay, so this system is not easy to come up with, and I would argue that once you learn the algebraic techniques, it would be much easier to solve this. But, whoops, we're done.